Thomas Stanley Curtis. High-frequency apparatus. All books on my channel are in public domain. Subsequent sections of the books are organized in playlists. Links provided in the last minute of the recording. Please subscribe, like and comment. Please be mindful that this book was printed in 1920. Some conceptions and units might be different from what is considered a standard today. Thomas Stanley Curtis. Chapter 1. The alternating current at low frequencies. While the manuscript for this book was being prepared, the author was approached by a caller who introduced himself as an enthusiastic experimenter and a reader of all manner of practical books. This gentleman explained that he was an armature winder by trade, and that he wished to take up high-tension work solely as a hobby. He was possessed of but little knowledge of mathematics and had been unable to understand the many books on transformer design and construction that he had purchased. A few minutes' conversation with this caller brought to light some important points which since have prompted a radical and wholesale change in the method of treatment. Half a dozen pointed questions suggested the introduction to the general subject that is offered in the next few paragraphs. What the alternating current is. An alternating current is one that periodically changes its direction of flow a certain number of times per second. It is the reverse of the direct current, which is assumed to leave the battery or dynamo at the positive pole and return by way of the negative pole. With the alternating current, the terminals of the machine are alternately positive and negative. This characteristic is well shown in the diagram, Figure 1. Which may be assumed to show the course taken by a current leaving the terminals of an alternating current generator having 4 field poles and having its armature or rotor driven at 1800 R.P.M. This machine would be termed a 60-cycle alternator because the current it delivers would make 60 complete cycles or 120 alternations in a space of 1 second. With reference to Figure 1, let us assume that A represents the current as it starts from one collector ring of the machine. Following the direction indicated by the arrow, we find the current rises in voltage until it reaches its peak at B. The value then falls back to 0 as the current returns to the other collector ring, C. At this point, the armature or rotor of the machine passes to the next set of field or stator poles and the current starts out over its circuit again, but in the reverse direction. For convenience, this is shown as below the 0 line in the illustration. Leaving C, the current rises to the maximum at D and then returns to E. The period of time taken in the passage from A to E is just 1/60th of a second. In this space of time, the current has made a complete cycle of 2 alterations, one in a positive and the other in a negative direction. In 1 second of time, it will have made 60 complete cycles. It is therefore called a 60-cycle current. Change of frequency. Now let us assume that the alternator be supplied with 8 field or stator poles instead of 4. As a reversal of current occurs when the rotor windings pass from the influence of one pair of stator poles to the next pair. It is obvious that to double the number of stator poles is to double the frequency, if the speed at which the armature is driven remains the same in each case. On the other hand, precisely the same result is obtained if the number of poles remains fixed and the speed of the rotor is doubled. Therefore, the matter sums itself up into a simple formula which will be useful to the worker if he will but understand it and not fear it as some intangible form of mathematics. This formula is, frequency equals 2 times 60 divided by RPM times number of poles. Therefore, if we know the number of poles of a given machine and the speed at which it is driven, we may multiply the number of revolutions per minute by the number of poles and divide this product by 120 to find the frequency of that particular machine. On the other hand, suppose we know the number of poles and we are required to produce a certain frequency from a given machine. We must determine the number of revolutions at which the rotor must be driven. Note here, there is an error in print of this formula. The formula should be RPM equals 2 times 60 divided by number of poles times frequency and not as printed on the screen. The author of the channel. To simplify the first formula into a form where it is ready for use at a moment's notice without any calculation, we may say that the number of cycles per revolution will be equal to the number of poles divided by 2. To use this, let us take the case of the 4-pole machine. 4 divided by 2 is 2. Therefore, the machine will deliver 2 cycles to every complete revolution of the rotor. If the speed is 1,800 revolutions per minute or 30 per second, the frequency is 2 times 30 or 60 cycles per second. Effects of change of frequency. For commercial use such as lighting lamps and operating motors, the 60-cycle current is in general use in the United States. Certain parts of the country still use 125 and 133 cycle currents, and in Canada the 25-cycle current is much in evidence. A change in the frequency of the current necessitates profound changes in the apparatus it is intended to operate. It is not within the province of this work, however, to touch upon the alterations necessary in motors in order that they may be adapted for various frequencies. Suffice it to say that in the case of transformers, which are closely identified with the apparatus described, Any change in the frequency of the current necessitates a corresponding change in the windings of the transformer. Generally speaking, one of the higher frequencies is to be preferred for transformer work, for the core may be lighter and smaller, and the instrument is consequently cheaper and easier to build. Therefore, if the worker intends to generate his own alternating current, he may well employ an alternator producing a 120 cycle current at moderate speed. As a rule, however, some form of alternating current supply is available and, in such event, the experimenter will, of course, find it cheaper and better to so design his apparatus that it will operate in a satisfactory manner on the circuit at hand. In the various descriptions of transformers which follow in later chapters, the data for all standard frequencies are given in order that the worker need not make computations unless he so desires. In addition to this, one entire chapter is devoted to a simple explanation of the principles of transformer design, and, from this explanation, the average worker will be enabled to work out any special design that may appear desirable. In the case of direct current supply, a motor generator of the type shown in Figure 2 is sometimes used. This consists of an alternating current generator driven by a direct current motor. Both armatures are mounted on the same